Okay, we're actually going to begin by going to the very last page. Let's look at example 25. Why do you think we're going to go over example 25 first? Anybody?
Does everyone know? You know. There's something.
There you go. Good job, Kazumi. We skipped all this stuff on day 3, unit 6, day 3. I wanted us to mainly focus on those word problems because this next test is about 40% word problems. We didn't go over this, so we're going over it now because you're going to want to need to know. You're going to want to know how to do it. And the stuff that we did skip on unit 6, day 3 that had this sort of stuff involved, I will shoot a video over that. I'll put it on unit 6, day 3 module, same module. You can go back and view them if you'd like to, if you just feel like you need a little bit of reteaching on that. Okay, whenever we graph, we normally graph, if we're going to plot points, we have an X coordinate, Y coordinate, or values that correspond to a particular coordinate. Whenever we're doing these types of problems, we have time as a factor. So we're going to have 3 different columns. We're going to have a T column, an X column, and a Y column. That says find the rectangular equation with restrictions. Our restrictions here are time. They say time, T, has to be greater than or equal to 0. So truly, you could start at 0 and go 0, 1, 2, 3, 4, 5. Those are the numbers I want to use. Let's plug them into my equations here, and then we can find X and Y. But slow down before you just start by saying, I want T to be 0, 1, 2. Look at your equations. Let's say T was 3. If I had to plug 3 in here, 3 plus 3 is 6. So the X value is 6. What happens if I plug 3 in here? You'd have to take the square root. I don't know what the square root of 3 is, or 5, or 7. So we want to use numbers that are perfect squares. So whenever you go to do this, check to see what your equations are. And if you have square roots, use perfect squares. So we want T to be 0. We want it to be 1, 4, and 9. Okay, so in order to figure out what is X at that particular point, we're going to take 0, substitute it here for T, and then do our math. 3 plus 0 is 3. Take 1, substitute for T, we'd get 4. 4, substitute for T, we'd get 7. And so on. Now to figure out here's what I'm going to do, because I get easily confused on this stuff because I forget that I have several different numbers, but we're only plugging in T values here, so I'm going to cover up X just for the time being. I want to substitute 0 for T, and that will give me what Y is at that point, once we do the math. So the square root of 0 is 0. We took 1 and plugged it in. The square root of 1 is 1. Square root of 4 is 2. Square root is 9. It's 3. And now we're going to cover up the T values. We don't need them anymore because we're just going to plot X and Y coordinates. So 3, 0 would be here. 4, 1. 7, 2. And then 12, 3 would be a little off of our graph, but that is okay. Now, whenever we're graphing these things on paper and we're trying to show motion, because these are parametric functions, we show motion simply by just drawing arrows continuously. It just lets us know which direction we're headed. Okay, before I continue on, let me just take care of some things that might be a little confusing with this. Scratch this out. Right here it says check your answers with the key on Canvas. Those of you that are in person, the key is on Canvas right now. If you wanted to work ahead of me and check your answers on the key via Canvas, you could do that. Feel free. It says right here, there is an extra review and key on Canvas as well. Liar. No, there's not. There might have been last year when we used this review, but not this year. Okay, now Y equals what? We have to figure out what the rectangular equation is that would produce this graph. Now, here's what you want to look for. We've been given 2 equations here. X equals 3 plus T, Y equals the square root of T. Whenever we graph a function, isn't it most of the time Y equals something, right? So let's not mess with Y for right now. let's go over here to X. What you want to do, I'm gonna get a separate sheet of paper here. Is the name of the game is let's get T all by itself. And the way that we would do that is subtract 3 from both sides, leaving us with X minus 3 is equal to T. Now that we know what T is, we're going to go back to that Y equals portion of our equation here and simply substitute. So Y equals square root T is X minus 3. And if you were now to plug this equation into your calculator, that's what you get. We have now found the rectangular equation with the restrictions of time here. All right, let's start with example 1. Determine if the directed line segments AB and XY are equivalent. These are pretty easy. I'm going to start by labeling X1, Y1. I just do this because it helps me most of the time not make a mistake. And then X2, Y2. We want to start with X2 first, which is 5, minus our X1 value of 1 to get 4. That represents the X portion of our component vector. Now that we're going to do the exact same process, except this time Y2 minus Y1. So 1 minus -5, 2 negatives. Going to change to positive. And now we have the Y portion of our component vector. We're going to do the exact same thing here with our X and Y sets of coordinates. Our second component vector is 4, -4. Are they equivalent vectors? No, but it have to be exactly the same. And they're not. That's it. That's all you have to do. I'm going to let you do 2 on your own. I'm now going to move on to example 3, if you'd like to follow along with me. Okay, first, find the component form of number 3, and then magnitude, number 4, of the vector. It's important to note what they have here. They have vector PQ. That arrow is indicating, and also the order that the letters are presented in, they're indicating what our initial point is and what our terminal point is. So our initial point P, that we could label X1, Y1. And then terminal point Q, we could label X2, Y2. You're going to need to know what initial means, what terminal means. Initial is beginning, terminal is end. Whenever we're finding component vectors, you have to do end minus beginning first, otherwise you're going to get it wrong. So let's find the component form. So 2 minus -4 looks like 6, and then -3 minus 5. And now we can find magnitude. Whenever we have our component vector here, finding magnitude is pretty simple. We have an X coordinate, we have a Y coordinate. To determine magnitude, we're going to take the square root of our X term and then square it. Add that to your Y term and square that also. We are allowed to use calculators on this test, so let's use it. square root. Looks like we have a magnitude of 10. Yes, go ahead. Let's move to example 5. Write the vector in component form. That right there, that's our magnitude of 45. So we would start with 45 cosine and then our angle of 170. And then 45 sine 170. Go to your calculator. Let's plug in the x portion first. (45 cosine 170). If you're following along with me, is there any need to plug in our y portion into the calculator? No, because there's only one of these answers that has an x value of negative 44.316. It's B. Yes. Okay, example 6. We have to find the component vector here. This point right there, that's our initial. Where the arrow is, that's our terminal. Or ending, this is the beginning. We have to do end minus beginning in order to get the correct component vector. So if you do that correctly, you should get -5, -3. To find the magnitude, remember, square root. Since it doesn't tell us where to round, at least I don't think, we're going to round to 3 decimal places. 5.831. And now we can determine direction. And before I start showing you how to do that, I'm going to give you this little cheat sheet right here. Reminder that will not be provided to you on your next test. Now, whenever we're trying to determine direction, the process is fairly simple. It's second tangent in your calculator, second tangent, and then y divided by x. Y, -3, divided by x, -5. But when you get your answer in your calculator, that's not always going to be your final answer. That's where this cheat sheet comes in handy. It depends where is your vector located, which quadrant. If it's in quadrant 1, then whatever answer you get in the calculator is your answer. If your terminal array is in quadrant 2, then if you do second tangent y divided by x, that should be a negative value. You would do 180 plus that negative value. Over in quadrant 3, 180 plus the answer in your calculator. And then if it's in quadrant 4, 360 plus the negative answer in your calculator. Now you might be able to tell based on the picture here where this terminal array is located. Odds are they're not always going to give you a picture. They might not ever give you a picture on your test. I don't know. But as long as we know the component form, it's as easy as plotting a point. I think we're all pretty good at plotting a point. So if I were to say on a coordinate plane, plot -5, -3, I think you could all do it. You'd go left 5 and down 3 units. So left 5, down 3. You'd plot your point. And then now if we wanted to graph our terminal array, that's what it would look like. So this vector is in quadrant 3. So whenever we do our calculations to find direction, whatever our answer is, we're going to want to add 180 to that. So the direction of the vector is, this is where we're going to start. Inverse tangent y divided by x. And then let's see what that is. Okay, we would get 30.96, whatever. But this terminal rate is in quadrant 3, so we need to add 180 to that answer. It gets to 10.964 degrees. Example 9, find the direction of V. Second tangent of Y. Divided by X. Okay, I have negative 10 points, some. Think about which quadrant this would fall in. So looking right here, if I had to plot this coordinate on a coordinate plane, we'd have to go right 44.2 units. So I'd have to go way over here and then down 7.8. So our vector is located in quadrant 4, and remember what the pattern of quadrant 4 is. It's right there. So we're going to do 360 plus, I'm going to scroll up and copy and paste my answer down. $349.992 degrees. Find the direction of vector V equals negative 3, 1. Now let's figure out what quadrant are we in here. We have to go left 3 and up 1. Left 3, up 1. So we're in quadrant 2. That's what we need to do for quadrant 2. 180 plus our negative angle theta. 80 plus. Copy and paste. 161.565 degrees. Example 11. For the following exercises, and then it gives you a set of component vectors. Find the component form of the resultant vector. So we're going to start by writing down what the component vector of U is, which is right there, negative 2, 5. And we are going to add that to the component of W. 2, 7. Now we want to add like terms. We have our X values here. So negative 2 plus negative 2. Negative 4. And then add your Y terms together. 5 plus 7. Get 12. That's your answer. That is the resultant vector for 11. Okay, 12, I'm gonna start setting that one up. I'm gonna start this one down by copying this component vector, because currently there's really nothing I can do with it just yet. Now I'm going to want to distribute this negative throughout the parentheses. But what I'm gonna do, so I don't make a mistake, is once I distribute that negative, we're then going to add our terms together. I would hate to distribute the negative and then write these components side by side without any signs symboling them, and then you make the mistake of multiplying. We don't want to do that. Right, so negative times -2, negative times 5. And like before, we want to add our x terms with x terms. So 1 + 2, -6 plus -5. And that would be our resultant for 12. And now 13, 2 times component vector u. Adding that to 3 times component w. Start by distributing the 2 throughout the vector here. So 2 times -2. 2 times 5 plus 3 times -2, 3 times 7. Okay, add your x terms with the other x term. So -4 plus -6. And then 10 plus 21. And we now have the resultant. Okay, example 14. A ball is thrown with an initial velocity of 67 feet per second at an angle of 41 degrees, but horizontal. Find the horizontal and vertical components of the velocity to the nearest tenth. Makes no mention of time, so let's not worry about that. So a ball is thrown with an initial velocity of 67 feet per second. So 67 cosine, and then the angle. 67 sine angle. Plug those in your calculator.
So how do I know in this equation you don't find t?
Correct. They make no mention of time. They're not saying something like, when will it hit the ground? Or how long will it take to reach the fence or something like that. Those are usually giveaways that we're actually needing to account for time. All right, a plane is flying on a bearing of south 25 degrees west at 342 miles per hour. Okay, I have a coordinate plane here. Let's see, we need to determine, well, what is the plane's magnitude or velocity or speed? They tell us it's 342 miles per hour. And then we also need to find the direction that the plane is traveling in. The bearing is going to help us do that. That's not the direction your plane's traveling in. Well, I mean, it is, but we don't use bearings whenever we're using component vectors. So south 25 degrees west from the southern point of our grid here, we would travel to the west about 25 degrees. Plot. And then draw your terminal ray. Now 25 degrees south, 25 degrees west, that is this angle here. So this angle is 25 degrees. The angle that we need is from here to here. Now, hopefully you remember that if I were to do a rotation from here all the way to here, that would be a rotation of 270 degrees. So we can do 270 minus that angle of the bearing. And that gives us the direction that the plane is flying. $245 degrees. Let me section this off just a bit. Okay, now we're gonna.
That's the bearing.
The bearing was south 25 degrees west,
Oh, yeah,
but that helped us determine what is the direction of the plane
okay.
in relation to the positive x-axis. Okay, a tailwind is blowing in the direction of north 33 degrees east. And it is blowing at 28 miles per hour. North 33 degrees east. So from the north, we'd rotate about 33 degrees towards the east. And then draw our terminal ray. 33 degrees. That is that angle here. But we need the angle here. So you could do 90 minus 33 to get 57. That's the direction of the wind, 57 degrees. Write in component form and find the actual speed and direction of the plane, and also state the bearing. So the component form of the plane would be magnitude cosine angle magnitude sine angle and we are going to add that to the component vector of the wind. Which would give us our resultant vector. When we go to add, make sure you're adding cosine with cosine in your calculator and then add sine with sine. Oops. Start that again, 342. Add that with 28. Okay, as a vector in component form, what we have here, that's what you would write here. In order to find direction Remember, this is our X value, this is our Y value. They want us to solve for speed first. I'm sorry, I'm getting a little out of order. Doesn't really matter, but I'm gonna follow along with the template they provided you there. So we found our component vector. We're now about to solve for our speed, which is gonna be square root of X squared plus Y squared. Oh, good. I was like, I think I just cleared out all my data. Square root. You're following along with me. Did you get 314.297? Good. That's our speed. And direction, we're going to use inverse tangent, second tangent in your calculator, and then y divided by x. Tangent, I'm going to scroll up and find my y value. Divided by my x value. Okay, to get 65.710. But what we have to account for is we have to think about, well, where would this plane fly in our quadrant here? That right there. Is that what you
I
got?
have a couple like numbers. I like
Did you use the
65.9.
rounded version?
Yeah,
That would be why.
because the one prior asked was nearest tenth.
Whenever you get your final answer round, but as you're working to get to the answer, don't use your rounded versions.
65.
So if we were to plot this point on a coordinate plane, we'd have to go left 129 units. So we have to go way down this direction on the x-axis and then down 286 units. So way down here, we would then plot our point and connect the terminal ray. So we're in quadrant 3. And that's the pattern for quadrant 3. 180 plus that angle that we just solved for. And now bearing. This is the direction the plane is flying. This direction that we just solved for, that is this angle here. So that rotation in orange is 245.710. The angle that we need for our bearing is here. So what we could do is we're going to take 270 minus, then let's copy that answer of our direction there. Copy and paste it. And that would give us an answer of this angle here. 24.290.
But did you say that was already 25?
Not necessarily. Now, let me finish this and I'll tell you why it's different, okay? All right, so this bearing here, start from south. We would then rotate 24.29 degrees to the west. So south. West. That's our bearing. Okay. So the question was, didn't we already state that the bearing of the plane was south 25 degrees west, right?
Yeah, and we also like, but those are numbers that are technically already given to us.
When you say technically, what do you mean? Is 24.290 technically the same thing as 25? Is that what you're saying?
Well, like we figured out, if you look at the plane graph that we did for the,
Okay, example 19, we're not solving anything. They are now making you aware that we are dealing with time now. And gravity. A kicker kicks a football with a velocity of 27 miles per hour at an angle of 42. Find the parametric equation that describes the position of the ball at t time. So x of t, remember, this is our horizontal positioning. 27 t cosine 42. And that is it. That's all they wanted you to do for. Okay, example 20. The distance a ball travels in t seconds is given by the parametric equation, and then it gives you the equations. What is the maximum height the ball reaches? Round in the nearest tenth. Whenever it asks for what is the maximum height, we're going to go to y equals, figure out your previous data, and then this is the portion of the parametric equation we want to plug in. The y portion, the vertical distance. There's a few different ways that we can solve for our maximum. This is the easiest. Just try and figure out what are your x-intercepts, and you don't have to be exactly accurate, just round. Looks like we have an x-intercept at 0. Looks like we have another x-intercept at 1. So second trace maximum, and then those intercepts, 0, enter, 1, enter, enter. The maximum height rounded to the nearest tenth, is that what it says? Would be 4.8 feet. (21) In the situation above, the wind is blowing against the ball at 35 feet per second. How far away will the ball be when it hits the ground? Well, let's first figure out when. When does the ball hit the ground? We've already graphed it. We want to identify what is the positive x-intercept. Looks to be right. It looks to be right at 1 to me. Let me look a little bit closer. Yeah. That x-intercept appears to go right through 1. So I want to use the x-intercepts that are to the left of 1, 0, and to the right of 1, 2, to help me solve this. Second trace. We're trying to find the 0. 0, enter, 2, enter, enter. So that's the x-intercept. 1.1, we'll round to 1.1. That's how long it takes for the ball to hit the ground. Now, if we were just trying to figure out how far will it travel, how far will it travel once it hits the ground, we would take this portion of the equation, horizontal distance, and we would simply substitute 1.1 for t. But we now have to account for wind. It says the wind is blowing against the ball at 35 feet per second. So we need to add that. Don't subtract, add. So 35 t cosine. Do you remember what angle we're going to use if wind is blowing against the ball? 180. There you go. What angle do you use if it's blowing with the ball? 0. Good. So if it's blowing against, 180. If it's blowing with, 0. And now simply take 1.1, substitute it for t, and then use your calculator. So now that we are considering wind, it's going to travel 9.4 feet horizontally. Okay, 22. A baseball is hit off the bat at a velocity of 65, and a height of 2. If the angle of elevation is 43 degrees, when will the ball hit the ground? Let's see. At a height of 2 feet. So we're going to add that after our minus 16t squared. When will the ball hit the ground? Let's plug this into our calculator, the y equals portion. And we're trying to figure out what our x-intercept is. It looks like our x-intercept is 2.8, maybe 2.9, meaning this graph intersects the x-axis in between 2 and 3. So we're going to use that to help the second trace. 0, 2, enter, 3, enter, enter. Okay, looks like the ball is going to hit the ground at 2.8 seconds, rounded to the nearest tenth. Okay, 23. A golf ball is hit at a velocity of 175 feet per second at an angle of 38 degrees. How high will it be after 1.6 seconds? Since we're solving for vertical distance, we could just simply use the y equals portion of our parametric equation. So that's the only one I'm going to write down here. And simply take 1.6, substitute it there, there. And as long as you plug in and solve correctly, you should get 131.4 feet. If the hole is 320 feet away, could the ball have made it to the hole? Why or why not? There are two different ways that you could go about solving this problem. I think the easiest one is to take our vertical distance here and let's plug it into our calculator. So what I'm trying to solve for is, well, when will this ball hit the ground? It looks like it's going to hit it 1, 2, 3, 4, 5, in between 6 and 7. So second trace, I'm going to find the 0 in between 6 and 7. So 6, enter, 7, enter, enter. It is going to hit the ground. .734 seconds.
About 7, like. They,
Do you have it now?
yeah.
Okay, good.
I think I know what we're.
Gotcha. Okay, now what we can do is, remember, this was simply the y equals portion of our component vector. We would need the x equals portion of our parametric equation. That way we could figure out how far it travels horizontally once it achieves 6.734 seconds. So I'm going to take 175 t cosine 38, and I'm going to substitute. Exactly how far will it be after 6.734 seconds? Let's find out. So once that ball hits the ground, it's going to be 928 feet away from where we originally hit it. It says the hole is 320 feet away. So could the ball have made it to the hole? Why or why not?
Yeah.
No. Way too much club. Yeah. So in the event that you don't play golf, here we are. We are about to hit the ball. Here's the hole. We know that's the hole because there's the pin. So if this is 320 feet, we ended up hitting it 928.631 feet. So I'll just put that over here. We said, quick. Bloop. No. We way overshot the hole. And that's your final answer.